In this lecture, we will start our discussion on particle image velocimetry. We have discussed about many flow visualization techniques earlier. If you recall, we discussed about smoke flow, dye flow visualization, etc. And in all such cases, we could extract qualitative details about the flow field. However, if we are interested in quantitative details of the flow field, those methods are not adequate. Let us say if we are interested in the flow field velocity, then we cannot get direct information about that from those measurements very accurately. Particle image velocimetry addresses the issue of flow field velocity measurement. This is a very useful reference. Two images have been taken from this reference to give you an overall idea about what particle image velocimetry tries to do. On the left side, you have a flow visualization conducted in a water tunnel, where you can see an airfoil pitched at an angle of attack to the flow. When water flows past it, the flow is laden with aluminum particles and it is illuminated with a suitable illumination source, and a video recording of the flow field is done. Later, the sequence of images are fed into a certain system which can transform it into velocity vectors. In particle image velocimetry also, the process is broadly like this. However, it has a lot of optics, lasers, electronics, video and computer techniques involved in the transformation from this to this. So, over the next few slides, over the next few minutes, we are going to discuss more on this. This is a schematic diagram of a particle image velocimetry setup in a wind tunnel. This is the wind tunnel test section. The flow is moving in this direction, and you have optical access provided at the test section, so that you can perform the particle image velocimetry measurements. What are the important constituents of the system? A laser, laser sheet optics, mirror, laser light sheet. The laser light sheet is the intended entity for which you have the laser, the optics and the mirror system. With the laser light sheet, you illuminate the flow. The illuminated flow helps us to visualize the tracer particles. And imaging optics comprised of cameras are looking at that flow and acquiring the images. The laser would produce sheets of light at very close intervals of time, one at time t, another at time t dash, separated by a very short time interval between the two. When we look at the entire image which is captured by the camera, then each image is again broken down into smaller regions like this, the shaded square region, and we are essentially zooming into those shaded smaller regions, which you will later learn are called as the interrogation windows, and the dots that you see in each image are basically the illuminated particles. When you apply a suitable technique to analyze the motion of these dots over a short period of time between two frames, then that helps us to build information about the velocity at which those dots moved, and therefore that carries information about the local flow field velocity. Here are some more diagrams of typical particle image velocimetry setups. when you have a two-dimensional PIV system or a stereo PIV system. We will discuss more about the different aspects of PIV systems like that in due course, and the pictures are taken from a very important reference. Again, it is a Springer Handbook of Experimental Fluid Mechanics. When we discuss about hot wire anemometry or laser Doppler anemometry, these are methods with which you can obtain very accurate velocity information as a function of time at a single point in the flow field. However, in particle image velocimetry, you look at a certain region, like you looked at a rectangular region which the camera was focusing at in the previous slide. With the help of that, you can capture the instantaneous flow organization, the structures in the flow field, which form what are called as the coherent flow structures. Such features can be captured by PIV, but cannot be captured through single point velocity measurements. PIV, as we mentioned already, is based on the measurement of displacement of small tracer particles which are carried by the fluid, and we look at the flow field over short time intervals as the flow field gets illuminated by using a laser based optics, and the tracer particles are sufficiently small that they accurately follow the fluid motion. They do not alter the fluid properties or the flow characteristics. They are just out there to help us acquire information about the flow velocity. The tracer particles are illuminated by means of a thin light sheet generated from a pulsed light source, usually a double head pulse laser system, and the light scattered by them is recorded onto two subsequent image frames by a digital imaging device, often a CCD camera. By means of stereoscopic imaging, it is possible to determine the three components of the flow velocity within the planar field defined by the light sheet. That means you can also get a limited extent of information along the third direction in the depth, which is not possible to do with a one camera system. That means if a planar region is looked at by two observing cameras inclined at a certain angle, then with that you can get a stereoscopic vision, very similar to how we do it with our own eyes. Two eyes can give us the depth information effectively. However, with a one camera system, what happens is it has the restriction that the optical axis must be aligned in the direction normal to the light sheet plane. This is a very restrictive situation. Moreover, such systems only yield two velocity components within the measurement plane and are therefore only suitable for investigation of flows with a negligible out of plane velocity component. That means, if the particles are moving along purely in the xy plane, then such a measurement is accurate, but if there is any velocity component along the z direction which is into this plane or out of this plane, then they would go out of the illuminated light sheet region altogether, and then there are inaccuracies which are produced. Such inaccuracies can be reduced when you do the stereo based imaging. PIV is essentially a non-intrusive measurement. However, it requires optical access. So, though you do not really need to put in a probe or need to put in an instrument for making the measurement, but still you have to make the test section of the wind tunnel having optical access. You need it both for the delivery of the light sheet. You have to make sure that the light sheet actually reaches the region where the measurement is intended to be done, and also for recording of the images. In order to obtain robust unbiased measurements of the flow domain, it is very important that the tracer particles are homogeneously distributed. They have to be uniformly distributed all over the flow within the observed flow region. This is a very distinct difference with respect to other flow visualization methods, because we have seen that for smoke flow or dye flow methods, we have looked at specific points through which those smoke or dyes were introduced into the flow field, which means that you are selectively looking at the flow field by using the fluid trackers, which are introduced at specific locations. But here, on the contrary, you are homogeneously seeding the flow field with particles. That means you don't have a preferential region or a preferential point through which the tracer has to be introduced into the flow field. The recorded images are typically processed offline on a digital computer, and this consists essentially of a cross correlation analysis of the particle image patterns in small subdomains or interrogation regions, which we talked about. If you remember that the camera image had a small region that was an interrogation region, you can imagine that the entire region of visualization by the camera is split into numerous such small regions, which are called as the interrogation regions or interrogation windows, and they are looked at for the first and the second image frame, and then they are cross correlated. Based on that, the velocity information comes up. So here you are looking at a typical frame where a small region shows you that interrogation region, and if you zoom deep into that region, what you see is something like this. It's laden with a few particles with specific locations. So if you look at the same interrogation region after a short interval of time, the particles would have relocated themselves, and then once you apply the cross correlation analysis on those two image frames between the first and second image, then what you end up getting is a calculation, a result coming out of that, which gives you the spatial correlation. Based on this spatial correlation, we are able to generate the velocity vectors. We will learn a little bit more on this in a subsequent lecture. Because of the stereoscopic viewing and the finite thickness of the light sheet, the observed particle image displacement is slightly different for each camera when you have multiple cameras looking at a certain region of the flow. Let us say you have two cameras, a left camera and a right camera, very similar to your two eyes, and then you can extract certain amount of information in the depth direction, and the observed particle image displacement is slightly different for each camera because they are looking at it from different angles, and that depends on the magnitude and direction of the local velocity. The three component displacement vector is reconstructed from the displacements observed by the two cameras individually. The particle image pattern displacement divided by the image magnification and the time delay between the laser light pulses yield the local fluid velocity. This process is repeated for the entire image domain, which yields the instantaneous velocity in a planar cross section of the observed flow. So, it is done for each interrogation window, and when you do it for all of them, you have the entire data for the image window. Sophisticated interrogation methods have been developed that make it possible to interrogate images at high spatial resolution and to determine displacements with high accuracy. And in modern day PIV analysis, typically 10 raised to the power of 3 to 10 raised to the power of 5 velocity measurements per image with a typical measurement accuracy of about 1% is possible. Let us look at some of the general features and aspects of PIV technique, which we have already started discussing in the last few slides, but we are re-emphasizing on them once again. As we said earlier, that it's a non-intrusive velocity measurement, and it works extremely well in certain situations like high speed flows which have shocks, because if you want to put in a probe, if you want to put in a measurement instrumentation in any high speed flow, it acts as an obstruction to the flow. It would immediately produce shocks and it will disturb the flow altogether. Similar is the situation if you make intrusive measurements in boundary layers close to the wall. Earlier we have shown that probes may be put close to the wall where velocity measurement can start right from the wall through the boundary layer thickness, but then we have to remember that that is an intrusive technique. So, no matter how slender the probe is, it is still disturbing the boundary layer. It may alter the state of the boundary layer as well. Such difficulties are alleviated, are removed, eliminated practically in particle image velocimetry technique. The little bit of intrusiveness which those particles introduce into the flow is trivially small compared to the other techniques. Indirect velocity measurement. So, what do we mean by that? We are talking about indirectly measuring the velocity vector by making use of tracer particles. So, we are actually measuring the velocity of the tracer particles, and from there we are inferring the velocity of the flow field. Now, these are added to the flow before the experiment starts. Let us say in two-phase flows, particles are already present in the flow, say air bubbles in water or liquid fuel droplets in air. In such a case, it will be possible to measure the velocity of the particles themselves. But if you are also interested to measure the velocity of the flow field, that also is possible by putting in additional seeding. It is a whole field technique, unlike single point measurements. So, this technique allows to record images of large regions of the flow in both gaseous and liquid media, and to extract the velocity information out of these images. Apart from PIV, there are certain few emerging techniques like Doppler global velocimetry and molecular tagging velocimetry. Only they have the capability of whole field measurements, but other than them, most of the traditional techniques of velocity measurements are basically based on point wise measurements. One good thing is that for single point based measurements, there is very high temporal resolution. That means, in the time space, you can have the data acquired at extremely high frequencies. The spatial resolution in PIV is fairly high. However, the temporal resolution, that means the frame rate of recording the PIV images, is still somewhat limited, restricted by technology limitations. Instantaneous image capture and high spatial resolution of PIV allows detection of spatial structures even in unsteady flow fields, but in future, if the image acquisition rates are enhanced further, then temporal resolution of PIV could be further improved. Velocity lag. Now, the need to employ tracer particles for measurement of flow field velocity requires us to check one thing very carefully, that whether the particles are very faithfully following the motion of the fluid elements. Usually, larger particles tend to get dragged with the flow, and therefore, they are not necessarily representing the correct information about the flow velocity. Small particles follow the flow better. As far as illumination is concerned, in air and gas flows, a high power light source for illumination of the tiny tracer particles is required in order to well expose the video sensor by scattered light. Why we use tiny tracer particles in gases and air is because without that, if the particles get heavier, they would tend to settle. This problem is much reduced in liquids because of the buoyancy effects, which are significantly higher there because of the higher density of the liquid. Therefore, larger particles can be comfortably used in liquids, and then much low power light sources may be used for illuminating PIV tracer particles when liquid media are required. Duration of the illumination pulse. Duration of the light pulse must be short enough to freeze the motion of the particles during the pulse exposure, so that you avoid blurring of the image. If the illumination duration is too long, light streaks instead of light dots would be formed in the image, and this would obviously lead to erroneous velocity field information. Time delay between illumination pulses. The delay that you have between the two pulses, one at time t, another at t dash, if you recall one of the earlier slides. they must follow two requirements. They should be long enough in order to determine the displacement between the images of the tracer particles with sufficient resolution on one hand, and they need to be short enough to avoid particles with an out of plane velocity component leaving the light sheet altogether between subsequent illuminations. That means if you have a little bit of z velocity component, then the particles which are ideally supposed to follow the xy plane, the plane in which the light sheet exists, they would leave that plane altogether if you expose for too long, or rather if you have too much of a time delay between the illumination pulses. Distribution of tracer particles in the flow. In qualitative flow visualization experiments involving smoke and dye, a certain specific region of the flow is made visible by marking a stream tube in the flow with tracer particles. This you have seen for smoke and dye flow visualization in particular. Now, according to the location of the seeding device, the tracers will be entraining specific areas of the flow which are of interest. For example, it could be the boundary layer region over a body or wake behind a body and so on. The flow structure and its temporal evolution can be studied by means of qualitative flow visualization. For PIV, the situation is very different. You need to have a homogeneous distribution of medium density required for high quality PIV recordings. No flow structure should be detectable in the raw images of a PIV recording of high quality. For example, if you look at these images, this is a low image density image, this is a medium density image, and this is a high image density picture. What we mean is the density depends on the number of particles which are visible in the pictures. So, the density of tracer particle images, in the case of low image density, the images of individual particles can be detected, and images corresponding to the same particle originating from different illuminations can be identified. Each one of them you can identify separately. Low image density requires tracking methods, and therefore, such images can be used in methods which are called as particle tracking velocimetry. When it comes to medium image density, so this is low, this is medium, and this is high. For medium image density, the images of individual particles can be detected very well. You can identify each particle extremely well. They are not getting cluttered as such. However, it is no longer possible to identify image pairs by visual inspection of the recording. You cannot track between two images a specific particle where it was earlier and where it is now, because it has sufficient density already. Medium image density is required to apply the standard statistical PIV evaluation techniques. That means, the medium density is what is best suited for PIV. In the case of high image density, what you see over here, it is not even possible to detect individual images as they overlap in most cases and they form speckles. This forms a technique what is called as laser speckle velocimetry. Number of components of the velocity vector. Due to the planar illumination of the flow field, only two in-plane components of the velocity vector can be determined in standard two-component PIV or 2D PIV. Methods are available to extract the third component as well using a stereo PIV technique or a complete three-dimensional volumetric PIV technique. When it comes to temporal resolution, though PIV has high spatial resolution, as we mentioned earlier, that it still has comparatively low frame rates, and with high speed lasers and cameras we should be able to further improve the time resolved measurements. Spatial resolution. The size of the interrogation areas during evaluation must be small enough for the velocity gradients not to have significant influence on the results, and it determines the number of independent velocity vectors and therefore, the maximum spatial resolution of the velocity map. Again, repeatability of evaluation. In PIV, full information about the flow velocity field except the time delay between pulses and magnification at imaging is stored at recording time at very early stage of data reduction. Now, this information remains as it is, and it can be used for other offline processings as well in due course. So, in this lecture, we introduced the basic idea of a PIV system, first through a schematic diagram and then through a brief discussion of the process and its salient features and aspects. More details would be discussed in subsequent lectures. Thank you.